Okay, so welcome back to another video. So in today's video, it's the first video on this channel. We have a little differential equation: dy over dx is equal to y multiplied by the square root of cotangent x. So one thing's for sure that you guys know, if you're taking your differential equations class, you should know that this is actually in the form of a separable equations. So the steps are pretty straightforward. You just set everything in terms of y from one side and x on the other side, and then integrate it from both sides. And then you want to find your function in terms of y, basically. So it's pretty standard. Maybe it looks kind of basic, but I wouldn't put that past it. Don't take it too lightly. I've seen some differential equations that get very, very ridiculous moving forward. But I think with this one, this shouldn't be that too complex. But hey, who knows? Let's see what happens. Now, just like the first step I said, we want everything in terms of y on one side and x on the other side. But then we would want dy associated with y and dx associated with x as well. So before I can do this, I know the first thing I can do is divide the square root of cotangent, or divide y to both sides, so I get dy over y, and then multiply the dx to get square root of cotangent x multiplied by dx. But integrating square root of cotangent x is a little bit difficult to work our hands with around here, so why don't we try something a little bit simpler, or rather I should say rewrite the square root of cotangent x. So with that, let me also state, we'll just jump into rewriting square root of cotangent x. So let's see, square root of cotangent x. Notice that by definition I can write this as cosine of x divided by sine of x. And then if I replace the square root with in terms of the exponents, so we get that this is cosine of x and then divided by sine of x. And then that's being taken to the 1/2. The exponent is 1/2. Simply because square root of cotangent x divided by sine of x is equivalent to cosine of x, or the square root of cosine of x divided by the square root of sine of x. They share that same exponent, so I can actually rewrite that and work this outside. But notice that, I'll just write it over the next line here. This is also can be equivalent as writing as sine of x to the negative 1/2, and then divided by cosine of x to the power negative 1/2. And then if I use the rules of exponents, that's sine of x divided by cosine of x to the negative 1/2 power. And simply it's just tangent x to the negative 1/2 power, or in other words, this is written as 1 divided by the square root of tangent x. Okay, good. So how about I replace our square root of cotangent x with our new rewritten form, 1 divided by square root of tangent x. So let's see, so far dy dx equals y divided by square root of tangent x. Okay, now I'll multiply the dx to both sides and then divide y to both sides so that we get our terms by itself. So we get dy divided by y, and then that's equal to 1 divided by square root of tangent x dx. And now from here I can actually integrate both sides. So this means on the left hand side I'll get a natural log of y. And then, well, let's not jump the gun there just yet. Let's actually take the indefinite integral of our right hand expression. So what I want to do here is, let's do a u substitution. So I'll write this in orange. So I'll let u equals 1 divided by the square root of tangent x. Now what I'll do is I'll actually square, or take square both sides. So that means we'll have u squared. And then on the other side, we get 1 squared divided by the square root of tangent x squared. That means this is just 1 divided by just tangent x. And then, let's see, I'll multiply tangent x to both sides and then divided by u squared. So we get tangent x is equal to 1 divided by u squared. And now we can differentiate both sides. So this means we get that the derivative of tangent x is secant square x dx, and then that's equal to, and take the derivative of this side in terms of u. This is just -2 divided by u cubed du. Okay, and now I'll just divide secant square x to both sides. So this is dx equals -2 divided by u square secant square x du. But we can use our trig laws to see that secant square x is actually equal to, well, let me write out this in full for a second. So we know that that's actually equal to 1 plus tangent square x, okay, and then du. We know that tangent x squared is equal to 1 over u squared. So if I square both sides to get what we want, and we can do that substitution, that means we'll get everything in terms of u. So this means this is equivalent to -2 divided by u cubed multiplied by 1 plus, let's see, square. So this is 1 divided by u to the power 4, and then du. Simply, I can actually distribute the u cube into here, so that means dx is equal to -2 divided by u cube, and then u cube divided by u to the 4th, which is just 1 over u. Okay, with that, now we can actually substitute some stuff. So let's see, we have 1 over tangent x, so that means that will be replaced with u, then substitute our dx. So then this means we have, on the left hand side, you do integrate this, you'll get that that's ln of y. And then we set that equal to the integral. So replace this with our new terms. This will be 1 over square root of tangent x. We set that's u, so it's u multiplied with our dx substitution, which is du. So then we have -2u divided by u cubed plus 1 divided by u du. What I'll do is I'll actually multiply a u to both the numerator and denominator, just simply because we can actually just get rid of the 1 over u in the fraction from the denominator. So this is equivalent. So -2u squared divided by u to the power 4 plus 1 du. Actually, there's a negative in front of the -2, so I'll factor that out, divide that to both sides, so that means the negative will end up on the left-hand side with the natural log of y. So the negative natural log of y is equal to, okay. So now from here, what I'll do is I'm actually going to add a 0 term from this numerator, so I'm going to add and subtract 1, but I'll also decompose 2u squared with u squared plus u squared. So simply u squared plus 1, and then we're gonna add that with u squared minus 1, and then denominator still is preserved, it's still the same thing. But what I can see is that we could use our rules of fractions, that we can actually split this into 2 different fractions of the same denominator, and then using linearity to take 2 different integrals. So really this is, so u squared plus 1 by itself, and then divided by u to the power 4 plus 1 du, and then that's being added with the u squared minus 1, then divided by u to the power 4 plus 1 du. So then from here, what I can do now is I can actually multiply and divide a u to the power -2. This will actually make things easier when we integrate some things. So I'll multiply u squared, or u to the -2, to both the numerator and denominator for both integrals. So that we have our new indefinite integral. So let's see, if I multiply u to the -2 here, so this is 1, then plus u to the -2, then multiply u to the -2 here, this is just u squared, and then plus u to the -2 du. Then add this, we do the same thing, so this is 1, that's minus u to the -2, and then over here u squared, and then plus u to the -2 du. Okay, so now what I'll do here is I'm gonna rewrite both our denominators so that the denominator contains a binomial square factor. So we have a binomial factor and we squared that, but we also have a constant outside of that. So really what we can do is this can be factored out into u minus u to the power -1 quantity square, and then you'll see that you'll get u square, or yeah, u square, then -2, and then plus u to the -2. But since we have that -2, we're gonna add the 2 to that so that the denominator still preserves. So we have the rewritten. So we have a new rewritten denominator for both integrals. So let's see. This is u, then minus u to the power -1 quantity square plus 2 du, and then we're gonna add this with 1 minus u to the power -2 with that same denominator as well. -1 square plus 2 du. All right, so now what I want to do from here is we both are going to do u substitutions for these two integrals. So let's actually do this one by one. So let's start with the first integral over here. So let me just draw some arrows. So over here, how about I let the new variable v equals u minus u to the -1. Okay, so then dv is actually just equal to 1, and then plus u to the -2 du. Simply, you just take the different using the power rule, and then you'll get the new exponent. Okay, how about we'll jump ahead and do this one as well. It's basically the same thing. So how about I let the new variable m equals just the same thing. It's u minus u to the power -1, and then dm is equal to 1 minus u to the -2 du. It's parentheses, so I forgot to put that, but actually, wait a second. Okay, I made a jump to conclusion a little bit, but this is just a little mistake over here. This is supposed to be a plus, and then over here, that's supposed to be a -2. So it works the same thing with the same denominator, but this is going to be written differently just because we're going to do u substitution like I just stated doing this, so it'll cancel out the numerator from here. That's why we want this denominator from this integral here rewritten differently than the other one, despite them sharing the same denominator from previously. Okay, so now that error is fixed, so I'll just go back. We'll let okay, so m is equal to u plus u to the -1, then dm is equal to 1 plus, or 1 minus u to the -2 du. And now it's coming together. You'll see that the numerators will cancel from here when we do our u substitution. The same thing from over here. So we get the new integral. So this is 1, and then divided by, with our new terms of v. So this is v squared plus 2 dv. And then over here, plus with the new integral, 1 divided by m squared minus 2 dm. And then for now, so far, that's still set to equal to -ln of y, but let's not worry about that for now. We already solved that left-hand side. We just want to solve the right-hand side. Okay, so over here, this is very easy to integrate. This is basically, you'll know once you see it that this is actually the antiderivative of this form is actually the arctangent. So the standard form of the derivative, or the antiderivative of a function in this form, 1 over v squared plus 2, we'll treat 2 as some constant, or rather, it's basically a squared set equal to 2. So 1 divided by v squared plus a squared is equal to 2, so that means a is equal to the square root of 2. Its general form for finding its antiderivative is basically 1 divided by a multiplied by arctangent of v divided by a. So this means this integral over here is supposed to be 1 divided by, so in this case, the square root of 2 multiplied by the arctangent of v divided by the square root of 2. And then we'll just write our integral from over here. See, m squared minus 2 dm. Over here, this integral we want to evaluate, what we're going to do is we're actually going to do some a partial fractions decomposition. So that means m squared minus 2. We can actually write this, the denominator can be separated as m plus the square root of 2. Then let's see, plus, then m minus 2. M plus square root 2 and then m minus square root 2. That's what I meant to say. And we set that our a and then b. Then we solve from here. So let's see, we use the butterfly method just to find our terms together. So minus square root of 2, then plus, that's supposed to be plus here, and a is over here. Minus square root of 2, set that equal to the numerator, which is just 1. You'll see that b, so let's see, if I set m equals the square root of 2, positive square root of 2, then this will cancel, this will, because it'll be just 0. Then this will be 2, the 2 plus, or the square root of 2 plus the square root of 2, which is 2 times the square root of 2. I divide by that, then we get that this is just 1 divided by 2 times the square root of 2. Then if I set, find for a, so if I set m equals negative square root of 2, that cancels. And then over here we're left with negative square root of 2 minus square root of 2, so it's negative 2 times square root of 2, divide that, so we get negative 1 divided by 2 times the square root of 2. Okay, we have those forms. Now, I could, because they share the same constant, and also the negative is in front of the a since that's the first term, so I can actually move it, or I can actually move some terms around. So because it's commutativity, that means the denominator m plus square root of 2, it's just going to go on the right side, and then m minus square root of 2, it's go on the left. So this term comes first and this comes second. Rearranging some things is the way I'm trying to go at. So anyway, so with this new integral, so I'll factor out a 1 divided by 2 times square root of 2 with our integral. So let's see, this will be 1, and then m minus square root of 2, and then minus 1 divided by m plus square root of 2, then dm. Okay, but that's not difficult to show that this is actually, its antiderivative is a natural log of the argument. So this means this is 1 divided by 2 times the square root of 2, then it's multiplied with the natural log of, I'll put absolute values just to denote positive integers, or positive numbers rather, m minus the square root of 2, and then plus ln absolute value m plus square root of 2. Okay, then you'll see that we can actually use our rules of natural logs. So let me actually rewrite back our with our arctangent. So arctangent, then input v divided by square root of 2. Okay, and then like I said, you'll see that we can actually use our rules of natural logs to rewrite some things. So this is actually supposed to be a minus right over here. That's a minus. Okay, and because of this, this is we can write this as under 1 natural log, and that will be with the division. So this is the natural log of, let's see, m minus square root of 2, and then that's being divided by m plus the square root of 2. And then this is an indefinite integral, so we add our constant c. Okay, so now next, what I'll do is I'll substitute our inputs of that, our input for v and m. But I'm gonna take a step further, and to make things like very nice and clean, you could say, I'll actually multiply a u to both the numerator and denominators for both our inputs of v and m, mainly just to get rid of the u to the -1 exponent. So if I do this, so if I multiply u to here for our v and m, so I'll get the following. So for v, this means we have u squared minus 1, and then also multiply a u to the denominator as well. So we get this is -2 multiplied by u. All right, then over here, this will be 1 divided by 2 square root of 2, then the natural log of, so I'll multiply u to both the denominator and the numerator just to cancel the u minus 1 term. So with that, so we have u squared minus the square root of 2 times u, and then plus 1, and then that's being divided by u squared, and then plus the square root of 2 multiplied by u plus 1. Okay, and then plus c. And now from here, we can just substitute everything back for u, which we said u was equal to 1 over the square root of tangent x, but simply we rewrote that that's actually equal to the square root of cotangent x, So I'll replace everything back into there. So let me see, right here is good. Yep. So let me rewrite, let me put back our negative ln of y, or rather, actually for now, let me just leave the negative ln of y for now before I make some mistakes. So we have negative ln of y. You guys can still see that. This line a little bit because there's like a light like somewhere around here. So I'll put this over here. We're almost done basically, so I don't need that. I don't need too much room. So negative ln of y equals to this whole thing, but we substitute back for u. We said u is equal to this, but we also rewrote that we rewritten this because this was also equivalent to the square root of cotangent x. So 1 divided by square root of 2 and arctan of, let's see, so u squared, so that means this is cotangent x minus 1, and then divided by square root of 2 times cotangent x, okay, and then plus 1 divided by 2 times the square root of 2, the natural log of, so this is cotangent x minus 2 times, or the square root of 2, oopsies, this is minus square root of 2 cotangent, well, okay, there's also square root of cotangent x, so rather the square root contains the input, the square root of 2, then cotangent x underneath that radical symbol, and then plus 1. Okay, and that's being divided by, so this is pretty much the same thing as the numerator, except over here this is supposed to be positive. So 2 cotangent x, then plus 1. Okay, and then plus c. And now the last step I'll do is I'll divide negative to both sides, and I'll just jump the gun and then actually just take the e base. So when I take the e base to both sides, we'll get that here. Let me do it this way. So I'll put e natural log of y, and give me a second to write all this down. Okay, so we'll see that we get that this is y is equal to, so notice that we have e raised to some function over here with some differences and sums. So really we can using exponent rules, it's a multiple of e to this function multiplied by e with this function, and then multiplied with e plus c, e to the power c. But notice that c is a constant, some arbitrary constant. So I can actually rename e to the power c, and we'll actually just call this a. And then now from here we get that this is multiplied by e to the negative 1/2 square root of 2. So nothing has changed yet. I say yet because something will change just about soon. Okay, and then now over here, e to the power this expression. Notice that e to the ln cancels. You can actually, well, before we get to that step, notice that there's 1 divided by 2, or 1 divided by 2 times square root of 2 in front of the natural log, so it's a negative 2, don't forget. So what I'll do is I'll move that back here to the exponents, but notice that there's a negative exponent, so that means if we distribute the negative exponents to both the numerator and denominator, simply their reciprocal flips and that exponent would now become positive, and then e to the ln, that'll cancel itself out. So this is being multiplied by, let's see, so we have now cotangent x out. This denominator will now be the new numerator. So 2 cotangent x, then plus 1, and then the new denominator will be what our previous numerator was, cotangent x minus the square root of 2 cotangent x plus 1, and then to the power 1 divided by 2 to the square root of 2. Okay, and there you have it. We have solved for our general solutions. Right over here, our general solution to our differential, or the separable equation over here. Nice. Right. Now that's pretty cool if you ask me.